In example 1, I'm going to sketch a graph of the inverse of the exponential function 2 to the x. First, just by examining the graph, I see that this thing passes the horizontal line test. Any horizontal line only goes to the graph at most one time, and that means this equation must have an inverse. So what I'll do is list a couple of things about this function. Maybe to start with, I know the domain is all real numbers. I can see that by looking at the equation. And the range is all positive numbers. It goes from 0 to infinity. So this will tell me something about my inverse function. But to add a little bit more detail, I'm going to list a couple of points on the graph. Like, for example, here, at -1, I know we get 1/2 for y. This is the point 0, 1. Here's the point 1, 2. Then we have 2, 4, and one more. This is 3, 8. These are very easy values to get. You just put -1 all the way to 3 in the function 2 to the x, and you solve for the corresponding y values. This means, since the first is an x and the second is a y, on your inverse function, you have to have 1/2, -1. The inverse is the thing that switches out your x's and your y's. So this is going to be the point 1, 0. This is the point 2, 1. Here we have 4, 2, and then 8, 3. So I switched all of my x's and y's. I'm going to plot these, and whatever I get from my graph is the inverse of 2 to the x. So let's see. If we're at 1/2, we get -1. At 1, we get 0. At 2, we get 1. At 4, we get 2. At 8, we get 3. And I think that's enough to get a general idea of what this graph looks like. The graph has to go through these points, so it's increasing as the x values get bigger, and it's getting really, really close to the y-axis as we go towards 0. So here it is. This is the graph of the inverse of 2 to the x. We call this a logarithm. A logarithm just means you have the inverse of an exponential equation. The notation that we use for it, since we're talking about the inverse, I'll put f inverse of x. We write log to represent logarithm. I put a subscript of 2 to represent that we're talking about the graph of 2 to the x, and I just open some parentheses to indicate that we're talking about a function. I would read this as log base 2 of x. So when I see that notation, I know I'm talking about the inverse of the function of 2 to the x. Maybe just a little bit more about it. I know what the domain and range has to be by looking at my graph, but it's also these two things flipped around. So that is, I know the domain is going to be from 0 to infinity, and the range is going to be from -infinity to +infinity. I can see that both from the graph itself and the fact that it has to be the opposite for my original function 2 to the x. So here it is, log base 2 of x. Now, just really quick, if I started with the function, f of x was equal to 3 to the x, it would look a lot like 2 to the x. The inverse for this would be called log base 3 of x. And all that notation means is you're taking the inverse of the function 3 to the x. And perhaps more generally, if you had any number to the x, and there was an inverse for this function, we would call it log base b of x. So I think of this as the function that switches around the x's and the y's of your exponential function. And we'll apply this in a couple of examples from here. In example 2, the point of this is to get comfortable with what the logarithm actually means. Again, this idea of switching around something from an exponential equation. So whenever I write something of the form y is equal to b to the power of x, you can switch this to mean x is equal to log base b of y. I mean, it's very confusing looking, but in a few examples we'll see how this works. I perceive this as, if you have an exponential function, you put an x in and you get a y back. If you're using the logarithm function, it reverses it. It takes that y value back to the original x value. So let's actually check that out with a couple of concrete examples. So I'll use log base 2 of 4. What does this equal? And you can type this into your calculator, but I actually want to try to figure it out using it as the inverse of an exponential function. So I don't know what this is equal to, so I'm just going to call it x. So it looks a lot like this thing right here. I'm putting 4 into the log base 2 function, and it gives me x back. To see what this is equal to, I'm going to take the exponential function 2, and what I'm going to do is put the x in the exponent and the 4 outside. So what this is doing is I'm taking this value and this value, I'm moving it over to a more familiar function, and I'm switching out the inputs and the outputs, the x's and the y's. So this over here goes in the exponent, and this up here goes outside, and I'm just trying to think of, well, what number makes this thing a true statement? And, oh, well, I know x is equal to 2. What this means is that log base 2 of 4 is 2. And the reason that's true is because 2 squared is equal to 4, this idea of going backwards from an exponential function. So let's try a couple of others. How about log base 2 of 32? What is that equal to? To figure that out, you go to your exponential function 2. What do I put in place of x so it's equal to 32? These two statements are saying the same thing. And if you think about it a little bit, hopefully it's something you can guess. I know the answer is equal to 5. What this means is log base 2 of 32 is 5. So this original question here is asking, what power do I raise 2 to get 32 back? And the answer is 5. Maybe if we change the base a little bit, that could give us a little bit more insight about what's happening here. So let's look at log base 3 of 9. What is this equal to? To understand, I'm going to go to the exponential function 3 and ask, what do I put into the exponent so I get 9 back? And here the answer is going to be 2, because 3 squared is equal to 9. What that means is that log base 3 of 9 is 2. How about a few more? So let's try log base 3 of 27. To figure out what that is equal to, what power do I put in 3 to get 27 back? And here the answer is 3. So log base 3 of 27 is 3. Maybe just a few others here. How about log base 5 of 625? To figure out what that is equal to, what exponent do I put in 5 to get 625? Hopefully it's going to be something that we can guess. So it can't be 1 or 2, because 2 would give me 25. Let's see, you can try this on a calculator. If I try 3, I get 125. That didn't work. But I tried 4, and if x is 4, I do get 625 as my answer. So log base 5 of 625 is 4. All right, let's try one more example. So I want to look at log base, let's choose 10 of, I don't know, maybe 1,000. We'll go with that. This is a very common logarithm, log base 10, which we'll be using in the next lesson. This is often just written as log of 1,000, so log 1,000. If you see this notation, it's referring to a base of 10. That's the one that appears on your calculator. So anyways, I call this x. So this is asking, what power do I raise 10 to in order to get 1,000 back? And again, you can guess this one here. It's not 0, it's not 1, it's not 2, but if you type in 3 for x, 10 cubed is equal to 1,000. It actually gives you 3 zeros. So I know x is equal to 3. What this means is that log of 1,000 is 3. It's basically just counting the zeros that appears in the logarithm. So this one you could actually try on your calculator very easily. You can hit the log button, type in 1000, and it should give you 3 back. But the idea of this example is to just understand how a logarithm works as an inverse of an exponential function. In example 3, I want to use the following identity to solve an exponential equation. Before I do that, I want to demonstrate that this identity is true just by picking a couple of values for the base, the value a, and the exponent of p. So I'm going to write log of 100. So this is log base 10, which we don't have to write. And we're going to put a 2 for my exponent p. What this statement says is a logarithm, we can remove the power and write it in front of the function. So this is equivalent to 2 times log of 100. To show that the left side is equal to the right side, I'm just going to simplify both sides. Okay, on the left, 100 squared is 10,000. You get 4 zeros. And on the right, I'm just going to copy down log of 100. And I'll write the 2 in front of it. Now log of 10,000 is 4 because there are 4 zeros that appear in 10,000. For log of 100, that's going to be equal to 2 because there's 2 zeros in 100. And it turns out that, well, 4 is equal to 4. So this rule basically takes us from something that has this 2 in the exponent to it being in front of the function. It basically gets rid of the exponent, which is why logarithms are useful for solving exponential equations. So let's go over to 2 to the x is equal to 64. Again, this is something that you can type into a calculator to guess your answer, but I want to just apply this identity to this equation. What I'm going to do is I'm going to take the logarithm of both sides of my equation. Kind of like if you would square both sides or take the square root of both sides or divide both sides by 2, I'm going to write log of 2 to the x is equal to log of 64. If the first line is true, so is the second. I'm just doing the same thing to both sides of my equation. The second step is now to apply this property where, oh, well, I have this x in the exponent, but I can drop it down to something outside of the function. So I'm going to write this as x log 2 is equal to log of 64. And log 2 is a number, so is log of 64. It's also just a number. We changed something from an exponential equation to a linear equation. To solve for x, it's going to look a little bit different, but we're just going to divide both sides by log of 2. And my answer is x is equal to log of 64 divided by log of 2. And I'm going to type this into my calculator just to see if it matches up with what I think the answer is. So let's see, log of 64 divided by log of 2, and I get 6, which is in fact what I expected. 2 to the power of 6 is definitely 64, so this process actually works. So we didn't really need this identity to solve this equation because it's simple, but if you have a more complicated exponential equation, it could be quite useful for getting your answer to that expression.